Now let's discuss about the power losses in transformer. Transformer power losses are classified as minor losses and major losses. And the minor losses in transformer are stray load losses and dielectric losses. And iron losses and copper losses comes under major power losses in a transformer. And of minor losses, stray load losses are further classified as stray load iron losses and stray load copper losses. Now let's discuss about the stray load copper losses. Stray load copper losses are because of localized currents, which means if suppose this is the conductor which is having an input of 100 amperes, let us suppose, and the output will be less than 100 amperes. This is because of localized currents. So to get the output equal to input, we need to minimize these localized currents. So to decrease localized currents, here stranded conductors are used. Stranded conductor means a conductor consisting of number of strands and all together forming a single conductor. This is called stranded conductor. So with standard conductors, if you give 100 amperes input, then we will get 100 amperes output. Therefore, the power losses which are occurring because of localized currents are called as stray load copper losses. And to minimize these stray load copper losses, we are going for standard conductors. And as these stray load copper losses depends on the current, so these loss comes under variable losses. Next, stray load iron losses. These losses occurs because of the leakage flux linking with the metallic parts other than the transformer core, that is bolts, nuts and transformer case, etc. And as these losses depends on leakage flux, so this stray load iron losses comes under variable losses. Next, dielectric losses. These losses are because of imperfect nature of the dielectric material, and these losses are due to displacement currents, and these losses depends on voltage. Therefore, as these losses depends on voltage, dielectric losses comes under constant losses. So of minor losses, stray load iron losses and stray load copper losses are variable losses, and whereas dielectric losses comes under constant losses, and stray load losses will be around 0.5% of full load losses, and dielectric losses will be around 0.25% of full load losses. So is why these losses comes under minor losses. And now let's discuss about major losses in a transformer. Iron losses are classified into two types of losses, that is hysteresis losses and eddy current losses. Now let's discuss about hysteresis losses. In pneumatic material, under normal condition, there will be number of domains which are randomly placed in the pneumatic material, and when this pneumatic material is excited from the external source, these domains will be aligned in a different direction depending on the excitation. So let us suppose that because of the input excitation, all the domains are aligned in this particular direction, and similarly for another type of excitation, the domains will align in a particular direction like this, and for another excitation the domains might be aligned in this direction. From this you must note that these domains will be aligned in a different direction depending on the excitation, and for their alignment they will consume some power, and that power consumed is called as hysteresis loss. That is power consumed for alignment of domains in a particular direction is called hysteresis loss. As the input to the transformer is AC, and let us consider 50 Hz frequency input to the transformer. So for every cycle there is one positive half cycle and one negative half cycle. So for positive half cycle input to the transformer, the domains in the transformer core will align in a particular direction. Let us suppose this. And for negative half cycle, these domains direction must be changed. Let us suppose to this direction. Means for one cycle these reversals of domains must happen, and for these reversals they require some power. That power consumed here is called as hysteresis loss. We seen the BH characteristics of transformer like this, and these BH characteristics are drawn for one cycle of the input. So for 50 Hz frequency input to the transformer, we are having 50 cycles per second. Means the domains in the transformer core must get reversed 50 times per second. And we can find out the hysteresis losses by Steinmetz formula, which is WH is equal to eta into B max power X into F into V, where eta represents the Steinmetz constant, and Bmax is the maximum flux density, and F is the frequency, and V is volume. As transformer core is made up of CRGO steel, for CRGO steel axes are having a value of 1.6, and this hysteresis loss for one cycle is equal to area enclosed by this BH curve for one cycle, which means that this is the area enclosed by the BH characteristics for one cycle, which is equal to the WH for one cycle. Means for F is equal to 1, and the number of BH loops depends on the input supply frequency. So for 50 Hz input we get 50 enclosed BH loops. During the operation of transformer, as we know that induced EMF is equal to 4.44 phi Fn, from which we get the relation phi is directly proportional to V by F. So during the operation of transformer, if V by F ratio is maintained constant, that is if B is constant, then from this relation WH is equal to eta into B max power X into F into V, where eta is constant and volume V is constant, and here B is considered constant, means B max is also constant, which means that hysteresis losses is directly proportional to the frequency. And the second case, if V by F ratio is variable, that is it is not constant, that is B is variable, then as we know that WH is equal to eta B max power X F into V. Let us consider CRGO steel, which means X is equal to 1.6, that implies WH is equal to eta into B power 1.6 max into F into V, and that is equal to eta into, in place of B let's write V by F, so whole power 1.6 F into V. That implies WH is equal to eta into V power 1.6 by F power 1.6 into F into V, which implies hysteresis losses is directly proportional to V power 1.6 by F power 0.6. And next, eddy current losses. which are directly proportional to the conductivity of core material. So to have less eddy current losses, we need to decrease the conductivity of core material. That is, we need to increase the resistivity of core material, and that is done by adding 3 to 4% of silicon in core material, that is 3 to 4% of silicon in CRGO material. But adding 3 to 4% of silicon content to the CRGO steel will not reduce the eddy current losses to much extent, and eddy current losses are reduced to much extent by laminating the core. So to have less eddy current losses, we need to decrease the conductivity or increase the resistivity of core material, and eddy current losses are much reduced by laminating the core. And eddy current losses W is equal to K into B max square F square into T square, where T represents the thickness of the lamination and K is constant. So during operation of transformer, if V by F ratio is constant, that is if B is constant, then eddy current losses. So if B is constant, the other constants are here, K and T. Therefore, if B is constant, W is directly proportional to frequency square. And secondly, if V by F ratio is not constant, that is variable, that is B is variable, which implies W is equal to K into B max square F square into T square. In place of B, let's take V by F. So V by F whole square F square into T square, which implies here F square gets cancelled, and now WE is directly proportional to V square. Therefore, if V by F ratio is not maintained constant, then eddy current losses are independent of frequency. Now let's summarize this. During the operation of transformer, if V by F ratio is constant, then hysteresis losses is directly proportional to frequency, and eddy current losses is directly proportional to square of the frequency. And if V by F ratio is variable, then hysteresis losses is directly proportional to V power 1.6 by F power 0.6, and eddy current loss is directly proportional to V square. And as these hysteresis losses and eddy current losses depends on the input voltage, so as input voltage is maintained constant, so these losses comes under constant losses. Next, copper loss of a transformer. Copper loss depends on the current flow in the winding and resistance of the winding. So copper losses is given by WC is equal to I square into R, where I represents the current flowing in the winding and R is the resistance of the winding. This is the schematic diagram of the transformer, which consists of primary winding and secondary winding, and R1 represents the primary winding resistance, and XL1 represents the primary winding leakage reactance, and R2 represents the secondary winding resistance, and XL2 represents the secondary winding leakage reactance. So as copper loss depends on the current and resistance, so transformer will have copper loss in primary winding and copper loss in secondary winding. Therefore, copper losses in primary winding is equal to current flowing in primary winding is I1, so I1 square, and resistance of the primary winding is R1, and copper loss of secondary winding is equal to current flowing in secondary winding is I2, so I2 square, and resistance of the secondary winding is R2. Therefore, total copper loss is equal to I1 square R1 plus I2 square R2. And sometimes for easy calculations and analysis, primary side parameters are transferred to secondary side, or secondary side parameters are transferred to primary side. And in this diagram, primary side parameters are transferred to secondary side, means R1 is transferred to secondary side, so it is represented with R1 dash, and XL1 is transferred to secondary side, which is represented with XL1 dash. And as now R1 dash and R2 are in series, they both can be added, and these two are together represented with R02. Therefore, R02 is equal to R1 dash plus R2. Therefore, no copper losses refer to secondary side is equal to current flowing in secondary winding is I2 means I2 square, and resistance of the secondary winding is R02, and this diagram represents the secondary side parameters transferred to primary side. So as R2 is transferred to primary side, so is why here R2 dash and XL2 is transferred to primary side, which is represented with XL2 dash. Therefore now copper losses referred to primary is equal to current flowing in primary winding is I1, so I1 square, and here R1 and R2 dash are in series, so which can be added and represented with R01. So R01 is equal to R1 plus R2 dash. Therefore copper losses referred to primary side is equal to I1 square into R01. Therefore the total copper losses in a transformer is equal to I1 square R1 plus I2 square R2, or I2 square R02, or I1 square R01. And it is known that with respect to load, current will vary. So with respect to load, copper loss also vary. Therefore copper loss is represented as X into I whole square into R, where X represents the loading. That is, for full load X is equal to 1, which implies full load copper loss is equal to I square R, and for half load X is equal to 1 by 2, which implies copper loss at half load is equal to, in place of X, 1 by 2, and 1 by 2 whole square is 1 by 4. Therefore 1 by 4 times full load copper loss. As here X is equal to 1, this represents the full load copper loss referred to secondary, and in this case as X equal to 1, this represents the full load copper loss referred to primary. Now let's find out the per unit full load copper losses, and let's refer to the secondary side. So per unit full load copper loss is equal to copper losses referred to secondary means I2 square R02, which is full load copper losses referred to secondary, by VA rating of transformer. And as here we refer to secondary, we can represent with E2 into I2, and I2 and I2 will cancel. That implies per unit full load copper loss is equal to I2 into R02 by E2, which is equal to per unit resistance drop. This is the important relation which we will get from the copper losses topic, and you can also equate this to the I1 R01 by E1. And the conclusion about transformer power loss is that transformer power losses are classified into minor losses and major losses, and stray load losses and dielectric losses comes under minor losses, because stray load losses will be 0.5 percentage of full load losses, and dielectric losses will be 0.25 percentage of full load losses. So that's why these two comes under minor losses, and stray load losses are further classified into stray load copper losses and stray load iron losses. These stray load copper losses are because of localized currents, and as the stray load copper loss depends on current, so stray load copper losses comes under variable losses, and stray load iron losses are because of the leakage flux linking with the metallic parts of the transformer other than transformer core, that is bolts and nuts and other metallic parts. And as the stray load iron loss depends on the leakage flux, so these stray load iron losses comes under variable losses. And now coming to dielectric losses, these are because of the imperfect nature of the dielectric materials in the transformer, and these dielectric losses are due to displacement current. And as these dielectric loss depends on the voltage, so dielectric losses comes under constant losses. And now coming to major losses, which are classified into iron losses and copper losses, and iron losses are further classified into hysteresis losses and eddy current losses. And as these hysteresis losses and eddy current losses depends on the voltage, so these two losses can be considered as constant losses. So iron losses are considered constant in transformer, and during the operation of transformer, if V by F ratio is maintained constant, so hysteresis losses is directly proportional to the frequency, and eddy current loss is directly proportional to square of the frequency. And if V by F ratio is not maintained constant, then hysteresis loss is directly proportional to the V power 1.6 pi F power 0.6, and eddy current losses is directly proportional to V square, and in this case eddy current losses are independent of frequency. And coming to copper losses, so copper loss is equal to I square R, So copper loss depends on the current flowing in the winding and resistance of that winding. And as copper loss also depends on the current, so copper losses comes under variable losses. And the important relation what we get from the copper loss is that per unit full load copper loss is equal to the per unit resistance drop. Thank you for watching. If you like this video, please like this video, share this video, and do subscribe to the channel. Thank you. See you in next lecture.